KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.com.
In this class, we start with the 15th problem, and this is the last class regarding electromagnetic induction numericals. Okay, right. See this, which is first we will discuss the first problem in this class. That is what problem number 15. See here, an air-cooled solenoid with length 30 centimeters, area of cross section 25 square centimeter, right? An air-cooled solenoid with length 30 centimeters, and area of cross section 25 square centimeter, and number of turns 500, carries a current of 2.5 amps. Full stop. The current is suddenly switched off. In a brief time of 10 to the power of -3 seconds. Full stop. How much is the average back EMF induced across the ends of the open switch? In the circuit. Full stop. Ignore the variation in magnetic field. Near the ends of the solenoid. Okay. Please try to understand the question. An air-cooled solenoid with length, right? It is the area of cross section. So these two are the parameters or the quantities related to solenoid. So in this air-cooled solenoid, this is the length and it is the area of cross section and number of turns also. And the current passing through the solenoid is 2.5 amps. Full stop. The current is suddenly switched off in a brief time of 10 to the power of -3 seconds. Full stop. How much is the average back EMF? Induced across the ends of the open switch in the circuit. Full stop. Ignore the variation in magnetic field near the ends of the solenoid. Right. Now, answer. See here. The magnetic field inside a solenoid of n turns. See the answer, The magnetic field inside a solenoid of n turns, length small l and carrying current I is, that is B is equal to mu naught Ni by L. This is what we know now. This is what we already know. B is equal to mu naught Ni by L. Okay. Here, if we are going to calculate the flux linked with n turns of the solenoid, then phi is equal to NBA formula. In place of B, we have to write this. Then finally, mu naught A n square I by L. Right. Here L is equal to 30 centimeters. That is what 0.3 meters, comma A is equal to 25 square centimeter. That is 25 into 10 to the power of -4 square meter. I is equal to 2.5 amps. N is equal to 500. N is equal to 500. Okay, right. Now, initial flux linked with the solenoid is, initial flux linked with the solenoid is phi I is equal to, this is the formula ma, and you have to substitute the given values, that is 4 pi into 10 to the power of minus 7 into 25 into 10 to the power of minus 4 into 500 square into 25 into, sorry, 2.5 ma, because here they have given no, right, it is not 25, it is, see here only it is 2.5 divided by 0.3 Weber, that is equal to 6.54 into 10 to the power of minus 3. So, if we complete this calculation, we will get it as 6.54 into 10 to the power of minus 3 Weber. Okay, right. Final flux linked with the solenoid. This is what initial flux, no. Final flux linked with the solenoid when you know the current is switched off. Final flux linked with the solenoid when, that is what, phi f is equal to 0. When current is switched off means phi f is 0, no. Right. Now, average back EMF, what he is asking, see this. See how much is the average back EMF induced across the ends of the open switch in the circuit, right. Okay. So, this is what average back EMF is, epsilon average is equal to total change in flux, total change in flux, that is this value ma. Total change in flux means this one minus 0, right. So, finally, we are getting this value only divided by total time. So, time is evla time, total time, see here, that is 10 to the power of minus 3 given in the question, 10 to the power of minus 3. So, this one divided by 10 to the power of minus 3. So, finally, we are getting average back EMF as 6.54 volt, 6.54 volts. Okay, right, full stop. So, this is what 15th problem. Next problem, that is what problem number 16. See here. Obtain an expression for the mutual inductance. Obtain an expression for the mutual inductance between a long straight wire. Okay. So, when the mutual inductance, right. So, obtain an expression for the mutual inductance between a long straight wire and a square of loop of side A, as shown in the figure. So, that is what this is the figure. Okay, right. So, from this, right. So, this is the figure, it is a wire and it is the square, right. It is the mutual inductance between these two we have to calculate ma. Here it is the straight wire and it is the square loop of side A, okay, right, square loop of side A as shown in the figure. Okay, right. So, we have to obtain expression, the expression for the mutual inductance, okay, right. Now, you please observe carefully here what is going to happen, right. First, there are two things ma, A and B in this problem number 16. There are two things, A and B. First, I will tell you, first we will discuss A and then we will go for B, right. So, you please be concentrate. First, A. See here, that is, you know, this is the picture is a part of question ma, this is the picture is a part of solution, okay, answer, right. See this. First, we are in a discussion about A. So, we are going to calculate mutual inductance between, right, mutual inductance between a long straight wire, and a square loop, okay, right. See here, a square loop of side small a. So, observe carefully and see the picture what I drew there. So, based on that you can get a conclusion. See this, it is the small amount of square loop, that is what I have written as dr. So, it is the distance from wire to loop, it is x, and it is the distance, small r is the distance from wire, that is what, a straight wire to the loop. Loop means not the total loop, the amount, the area, the amount of area what we assumed. See here. Okay, right. Now, as shown in the figure, this is the figure. Consider a rectangular strip of small width dr of the loop at a distance smaller from the wire. At a distance, this is the small width, the distance of small width from the wire is smaller, right. Now, magnetic field at the location of the strip, magnetic field at the location of the strip B is equal to mu naught I by 2 pi r, mu naught I by 2 pi r. This is the magnetic field. Magnetic field at the location of the strip B is equal to mu naught I by 2 pi r. Now, this field, right, this field points normally into the area of the strip, that is A is equal to small a into dr, right. See, observe carefully. This field points near, this field points normally into the plane of the loop, right, that is the statement. Now, see, this is, I didn't write here, but I am saying, this field points normally into the plane of the loop. So, plane of the loop means this is the plane of the loop, right, into the plane of the loop. Now, area of the strip A is equal to small a into dr, small a into d into small r. Now, magnetic flux linked with the strip d phi is equal to B into A, that is equal to mu naught I by 2 pi r into A dr. So, A is equal to A into dr, no, that only he is writing here, that is A into dr. Next, total magnetic flux linked with the square loop, total magnetic flux linked with the square loop, phi is equal to integration d phi, no, see here. So, afterwards, in place of d phi, we have to write this value, and then take it the things which are constant, and we are integrating from r is equal to x to the r is equal to x plus a. This is the value 1 by r into dr. So, 1 by r you can write it as r power minus 1, and you can also use the formula, that is log x, integration 1 by x dx is equal to log x formula, that is what here ln into r. So, applying the limits, and finally the phi value, that is total magnetic flux linked with the square loop, we are getting mu naught I a by 2 pi into ln log 1 plus a by x, 1 plus a by x, okay, right. Next thing, see here. So, this is what A we discussed. Now, B. First see the question and then we will go for answer. Now, assume that the straight wire carries a current of 50 amps and the loop is moved to the right with a constant velocity v is equal to 10 meter per second. Now, assume that the straight wire carries a current of 50 amps, and the loop is moved to the right with a constant velocity, v is equal to 10 meters per second, Calculate the induced EMF in the loop at the instant when x is equal to 0.2 meters. Take A is equal to 0.1 meter and assume that the loop has a large resistance. Now, see here. So, first you try to understand the question. So, he is saying that the straight wire carries a current of 50 amps and the loop is moved to the right with a constant velocity, right. Calculate the induced EMF in the loop at the instant when x is equal to 0.2 meters. Take side as 0.1 meters and assume that the loop has a large resistance. Okay, see here. The square loop is moving in a non-uniform magnetic field. The square loop is moving in a non-uniform magnetic field, right. The magnetic flux linked with the loop at any instant is, phi is equal to mu naught I by 2 pi A That is whatever we got here, that only he is writing. And now induced EMF set up in the loop is, this formula, epsilon is equal to minus d phi by dt. That you can write it as like minus d phi by dx into dx by dt. Dx by dt means v, no. So minus v into d phi by dx, that is equal to minus v into d by dx. It is phi value is this one, sorry, this is the phi value. So after completion of that, finally mu naught by 2 pi into a square v divided by x into x plus a. So here we have to complete some mathematical procedure, So if you complete the mathematical procedure, finally we are getting this one, right? After completion of the mathematical process, here we are getting epsilon as, right? Epsilon as like this, that is epsilon as this value, and here you substitute, okay? Here you substitute, that is what induced EMF, no? So in this relation you just substitute, in this relation you substitute that value, that is mu naught by 2 pi into a square v into x divided by mu naught by 2 pi into a square into v by x into x plus a, right? So now we have to substitute the values, which is 4 pi into 10 to the power of minus 7, 2 pi is a constant, and a means 0.1 whole square, v is 10 divided by, it is 0.2 into 0.2 plus 0.1 into 50, I is there, no, right? So if you complete this mathematical process, mathematical calculation, then we will get it as 1.7 into 10 to the power of minus 5 volt. Phi value, epsilon value, right? Epsilon value as 1.7 into 10 to the power of minus 5 volt, right? Next problem number 17. A line charge lambda per unit length is lodged uniformly onto the wheel of mass capital M and radius capital R, full stop. The wheel has light non-conducting spokes and is free to rotate without friction about its axis, right? So they also given one picture, right? Now a uniform magnetic field extends over a circular region within the rim. A uniform magnetic field extends over a circular region within the rim, okay, right? Now it is given by b bar is equal to minus b naught into k cap. So where r is less than or equal to a is less than or equal to r, and in one case, in another case it is 0, Now the question is, what is the angular velocity of the wheel? After the field is suddenly switched off, right? So we have to calculate angular velocity of the wheel. See here now, see the answer. And it is a Faraday's second law of electromagnetic induction, no? So according to Faraday's laws of electromagnetic induction, the induced EMF epsilon is equal to minus d phi by dt, right? Next, this implies that the presence of an electric field, right? This implies that, see here, up to here clear, no? Okay, I will repeat once again, no problem. See this. The question is, a line charge lambda per unit length is lodged uniformly onto the wheel of mass capital M and radius capital R, full stop. The wheel has a light non-conducting spokes and is free to rotate without friction about its axis, full stop. A uniform magnetic field extends over a circular region within the rim. It is given by, right? So it is based on the condition. Now it is the figure related to this. He is showing this information you can get from this picture. It is A and it is capital R. Right now, what is the angular velocity of the wheel after the field is suddenly switched off? Okay, this is a question. So this is what we have to calculate based on the given data and this picture also. Now, it is from Faraday's laws of electromagnetic induction. Now, this implies the presence of an electric field E bar tangent to all points of the boundary of the circular region of radius small a. This is what? This is a small circle. Dotted lines, see here, dotted lines, right? That is. Now, if we move a test charge q once around this boundary, a work QE will be down. A work QE will be done. Full stop. The electric force on the charge is QE, and work done by this force round this boundary is QE into 2 pi A. QE into 2 pi A. Equating the two works done. So QE is equal to, equating the two works will be done. So it is what in this case, which is a work QE. This is what, not it is E, it is epsilon. So it is what Q epsilon will be done. Afterwards, the force is okay, it is QE, and work done by the force is QE into 2 pi A. Equating the two works done, we get, right? So this amount of work and this amount of work we are going to equate. Then finally Q will get cancelled. E is equal to Q by 2 pi A. E is equal to Q by 2 pi A. As epsilon is equal minus d phi by dt. As epsilon is equal minus d phi by dt. You know, E is equal to minus 1 by 2 pi A into d phi by dt. Right? So E is equal to minus 1 by 2 pi A into d phi by dt. Next, so it is what here we got it, no? Here we got that capital E is equal to Q epsilon is equal to QE into 2 pi, you know. So QQ will get cancelled. What is the answer here? E is equal to epsilon by 2 pi A. And we know this formula from Faraday's laws of electromagnetic induction. So that E is equal to minus 1 by 2 pi A into d phi by dt. So this value we are writing here. Now, so this is what d by dt of phi means pi A square B. You know that phi is equal to BA, A is equal to pi A square. Pi A square B, that is equal to minus A by 2 into. So we have to complete this differentiation. Then minus A by 2 into, which is what, dB by dt. Now we are using that concept F is equal to MA, force, that you know, that is equal to M into dB by dt, no? So this side F is there, this side, that is what E is there, no? This side E is there, okay. This side minus A by 2 into dB by dt, okay, right. Now see this one. First I will explain you the information and then I will go for calculation. See here. In the given problem, total change on the rim is equal to lambda into 2 pi A. Therefore, the force on this charge is F is equal to lambda into 2 pi A, right? That next F is equal to lambda into 2 pi A into E. So E value already we know here. Now minus lambda into 2 pi A into A by 2 into dV by dt. Okay, is it clear? Now in place of F we are writing M into dV by dt. It is F is equal to MA formula, Newton's second law of motion. Okay, right. Now in place of F we are writing M into dV by dt, and this side it is as it is, minus lambda into 2 pi A into A by 2 into dB by dt. Next, M into d by dt, in place of V we are writing R omega, because he is asking to calculate angular velocity, is equal to minus lambda into pi A square into dB by dt, right. Next, d omega is equal to, so we have to take all these things to that side, then minus lambda pi A square into B by minus lambda pi A square by MR into dB. Now this we have to integrate on both the sides, that's you already know. So to get omega from d omega, we have to integrate, no, right. So if we integrate this expression, then we will get omega value as minus lambda pi A square into B divided by MR. Okay, right. What is the direction? So regarding the direction we have to write like this. omega bar in vector notation, omega bar is equal to minus b pi a square lambda divided by small m into capital R into k cap. So when I am writing k cap, you can easily understood, right? And minus is there. Minus is there, there k cap means almost all you can conclude that the negative sign indicates that the vector omega bar is in the negative z direction. Omega bar is in the negative z direction. Okay, right. In this class, we discussed 3 problems. Problem number 15, 16 and 17. Okay. With this class, we completed all example problems, exercises and additional exercise problems from electromagnetic induction chapter. So in our next class, we will start a new chapter to discuss numericals. Thank you.